Thank you. Hello. Yeah, hi, good morning. So today we are going to discuss one of the interesting topic called is how to develop your extension in Postgres NC. So part of this topic, we are going to talk about what is an extension is and what is the need of extension in Postgres, and if you want to implement extensions, right? So we need to understand how does our Postgres architecture looks and where does this extension fit inside that, right? So let's begin that part. So what does extension mean for us? So you can consider extension is it's a plugin on top of Postgres and who gives some extra capability to the Postgres, right, without you modify the core engine part. Okay, so you can if you take it analogically how a Postgres extensions like in your smartphone you use Android or iOS, right? So you iOS or Android gives some basic facility to you, right? Some calls, you have messaging, you have cameras, right? But you need some extra capabilities to your smartphone without modifying your this iOS or the Android phones. Why do you do that? You just install the app from your Play Store and use it. So you can consider the extension is like that. Okay, so but when I say it's an extension is a plugin, it doesn't mean that it is something outside of the Postgres core engine. It's a part of core engine, but it uses the Postgres memory, the Postgres processes and the whole query pipelines. And the same time, when we say we are going to develop it from extensions, so it means that that we are not writing any wrapper, okay, around the Postgres, but that I mean here is we will write the code who will be sit inside the database and try to use all the capabilities and try to give this all capability to the Postgres database. Okay, so let's understand why do we need extensions. So the basic principle of Postgres is they want the Postgres core should be remain stable, generic, and lightweight. Okay, and it should be more it should be reliable to each and every users. Either it's a simple application who use Postgres to a company who is a bank who is doing a lot of billions of transactions to the transactions to a system where a terabytes of data you are storing for the image processing. For everybody's Postgres engine need to be more reliable. So in that case, if you keep adding new and new concepts to the database core engines, things becoming more expensive, it's code becoming more bloated. It's difficult to maintain those things, right? That's the reason why Postgres come with a very beautiful idea called as extension infrastructure, right? Part of that, you no need to do any changes to your core logic. So what you need to do is they given it some infrastructure, use that infrastructure and try to implement your things, and those innovation you can start contributing to those extensions developments. Okay, and so that your engine also becoming stable and core engine is becoming more reliable, and as I told you, it's more flexible and generic. At the same time, you innovate your new things, whatever you want to do with your extensions. So I could give an example where this extension is so powerful. Today, like this AI era, like you see. PG vectors is one of the important extensions developed on top of the core Postgres. Okay, and we have PostGIS, we have something called as head store for key value store. You have PG stat spend, mostly the DB used for the all the statistics, query level statistics calculations, right? So this is how extension give a all powerness to the Postgres. So I can tell in a single statement like extension make your Postgres more flexible, powerful and adaptable, so that you without compromising your core instability, you keep innovating your new things. Okay, so let's understand, like if you want to develop an extension, what are the things I need to know about that, right? So for that we need to understand the Postgres architecture. So we know that Postgres is a multi-process concept, right? Where when you use PGCTL command, the first thing the first process got started is called as postmaster. As some people say, it's a Postgres server process. It's the first process got started up. Who initiated is all the shared memory necessary for the system. So those major shared memories are like buffer pools, you have wall buffer, you have commit logs. Along with that, it starts some of the important processes, those background processes like those background writer, you have check pointer, auto vacuum process, wall writer, your block collector, right? Along with that, you can see in the storage, you can see those data, whatever you have, get stored in the disk, and those data will be in terms of data files, and data files are divided into pages, and this is how your data gets stored. When client connect to the Postgres, a dedicated process backend process gets created, and the backend process basically show up to the client. And when client execute any query, basically it use the pipeline of the query pipeline, that is nothing but your simple parser, analyzer, rewriter, and planner and executor, load the corresponding trees from the disk to the shared buffer pool. This is nothing but a cache, and where you do your read and write operation of whatever you do in the transactions. But now coming to the picture, when I'm going to develop an extension, where does my things fit? So this is what the first I have marked. Maybe it's more than that, but I'm just concentrating for the places we can implement our extensions. So let's talk about each of the stars and understand how does they fit our extensions. So one of the places I have put it is a backend process. So this is the place your extension implementation go here. So basically, when you consider an example, you have developed an extension for new data type supports. Okay, so those new data for the new data type supports, you basically give some functions to the user, right? So are there some views to the user, right? For that, so those implementations will be in this backend process code. Okay, so those implementations, so this will be loaded once you use this create extension name. Those of the implemented function get registered in this to the system, so that user can start using those. There is another interesting area where you can implement is called the query pipeline. So in the query pipeline, one of the interesting things you can do is you can you start hooking you to the query pipelines. So when you start hooking your pipeline, you can start intercepting to the query flow, and you can do the inspection of the query what is running in the systems, and you want to do some amount of modification, measurements, whatever you want to do in the query inspection time, right? You can do in this query pipeline. So this is the powerness you can do with, you can do with your extensions. Along with that, so consider a situation your extension want some amount of global awareness. Every session should know that what you are doing is you want to be aware of those things. So you can have you can implement your own shared memory who will be sitting near to you have the shared buffer pool or the wall buffer. So those is the area you can implement your own memory, and those that is specific to your extension point of view. Okay. Similarly, if your extension need a demand like you want to do some monitoring or you want to do some amount of cleanup or some amount of aggregations, so you can have your extension implemented background workers who will be basically sitting, one of the star called as writer process, whatever I have shown in the previous. So it can sit near to that place. Okay. So now coming to let's see the next part. Like how does the structure, when I going to implement an extension, how does the structure looks like? So so consider I am going to implement an extension. So so in the future slide we'll see like we'll take one specific example, okay, and taking that example we'll try to implement one of the extensions. So the extension is called as vacuum. Consider the extension name is vacuum booster, and the structure of this, once we implement it, the structure looks like a few bunch of files, a control file, a SQL file, the real core engine of your your extension, and the make file to compile this entire things. So if you see this control file is an ID card who basically tell the system, or when I say system, it's about the Postgres that who am I and what is my identity, those information. So we'll see these details when we start developing these extensions, okay, and we'll see there is another call is SQL file where we provide the interface, those implementation what we written in the C and what exposed to the user to use it in terms of view, tables, or a store procedure like that. So those interfaces are mentioned in this .SQL. So we call this a bridge between user and with our core logic. Whereas the .c file is the implementation where we really implement the core logic related to the extensions, okay. And as I told you, this need to compile and need to be created a a SO. For that we need a make file to compile it and get this SO. So this is how the entire structure of your extension looks like. So let's say this extension, when does get loaded and where does this SOs are stored. So when you see the typical Postgres installations, right, you can see like there is a special folder called a lib folder. In this folder, basically your SOs, the extension whatever you created will be kept it in there, or it can be by Windows, it will be DLL, and those two typical file, control file and the SQL file, will be under the directory called extension directory. This is under the part of share folder. And how does this get loaded? So the moment you before you start your Postgres, in one of the configuration in the Postgres config, you can give, there is a parameter called as shared preload library. In that you need to tell this is the extension, you need to load it. So when you start Postgres, the first process, as I told you in the process architecture, is the postmaster get started. It's the things he load is the your shared memory in the particular process. I mean the SO get loaded, and it searches for the keyword called the special function called is underscore PGNet. This is the entry point. You have to give a registration to the postmaster, right? This is the I am the extension. I need some registration with you so that later part user can use me. Okay. So in this PGNet, you basically informing to the postmaster like, see, I need some shared memory for me, because maybe I need for my some global tracking purpose, I need some workers to monitoring purpose. So we'll see that how we can link this all things together with an example. So we tell like in which place on the query pipeline we want to hook to the pipeline so that I can start observing my queries. So all detailed registration you do in the PG init functions, okay. And then the third part is that the moment user use create extension, create extension name. So those interfaces that you given to the user in terms of that SQL whatever I have mentioned, one of the more file, right? There you are mentioning the implementation and the SQL interfaces. Between this, there is the interface you provided so that user can access my, he can talk with my extensions. Okay, this is what the third phase. Okay. So let's take one a typical example, okay. So and try to solve this one of the typical problems by developing extension for that. So we know like the work of auto vacuums, right? So the typical, if you just to tell you what auto vacuum does. So auto vacuums basically is a dedicated there is a typical launcher process for auto vacuum who will be keep monitoring, right, entire database system to see like who are the, he will keep scanning your database and keep checking, and he is using some technical pooling techniques, and every nap time he comes up and see who are the database tables are get bloated. And when they reach to a threshold, suppose they reach to a 20% threshold, then what they do is the launcher start a special vacuum worker who will do the cleanup of your dead tuples. That is how vacuum works, right? But this type of situations are actually designed because Postgres, why he have done is like. This, if you remember at the start of the slide I told you, like it's Postgres want a generic logic. It cannot be, it should be common, it should be reliable to every type of systems. That's why they have used this pooling and napping type of concepts, okay. But consider a situation, okay, you have a application or a high load, high velocity workload, and where high amount of bloating is coming to the systems. And if you act like this, where you are, you take a nap and come up and see scanning and see that, oh, there is table bloated, you react, the moment you react, already the bloating started and your performance start degrading, okay. So these are the special case, you need to think something called as, instead of, instead of reactive mechanism, if you see some techniques called proactive mechanism, so things can move faster, right? So this is the proactive mechanism. We will try to solve it using our extension. Okay. The second part is, if you see today, even if the auto vacuum launcher, how does it know that we have dead tuples in the system, or how does it know that tables are bloated? It basically reads something called from the shared memory. It have something called we have something called statistics about the tables. So before PG15, it was everything is read from disk, which is more costly, and there is a special dedicated process called log collector used to collect those statistics, which is used to maybe because of the UDP calls, they may be used to lot of data loss used to happen, and some amount of lags should happen because of you have to read some of the disk, right, which is causing issues. But now what PG15 onwards they have done is, like, they have improved the performance by putting everything in those statistics in the shared memory, which is improve the performance. But if you see these typical situations where the system is now it's a highly loaded system, a high velocity system, where the works are like heavily operating on the they are creating a lot of bloatings in the systems. If you just do alerting, you just say that, oh, I have got a lot of dead tuples, it may not be enough, right? So when accounting is doing good, but it never alerts us that there is really problem happening. You have to take immediate action of those cleaning those dead tuples. So in this type of system, we are missing those alerting systems, right? Alerting as well as the event-driven techniques, because it is not proactive. It's just reactive and just further move it. Now the third part is, I'm just taking one of the study is, so today if you see cloud systems, they provide a lot of infrastructure for you, right? You have, the CPUs are becoming more and more cores, you have RAMs is used, and you got disk is becoming the operations becoming more faster. So if you see typical auto vacuum, just move again back to the auto vacuum techniques. If you see the auto vacuums, it create workers and he hand over the workers to do some cleanup. But if you see worker again, for him also some amount of cost limit is maintained. Now what is cost limit is, every worker is, what they are doing is, they are scanning the pages of each and to clean these dead tuples, right? So they need to scan the pages. So they have to read and write those from the disk. So the idea they Postgres have maintained is because typical HDD, those slow moving spinning devices, those read and writes is very expensive in terms of milliseconds. So why they thought is because if you see a typical vacuum operations, they are basically maintenance works who need I/O cost, right? So what they thought is, no, if you consume a lot of time in the I/O for this maintenance task, what about my queries who are running parallelly at the same time? I cannot make them to wait it, right? So that user feel like performance is very it's going degrading, right? That is the reason why we have a concept called cost limit. But in this special case where you have modern architecture, where the modern hardwares, you have, and even if the today's disk becoming NVM based disk, where the data instead of read and write can happen within microseconds, right? If those type of system, if you consider if you put this type of cost limit, you unnecessarily putting your, you reach the cost limit within the fraction of microsecond, then you are putting my, my worker to go for a sleep, the cost delay, the sleep you in terms of millisecond. If you see, most of the time my worker is not doing cleaning, he is going for a sleep. So what I am doing is, I am unnecessarily, now I am putting my disk, the resources in ideal situations. So these are some of the problem area, I'd say, like in this particular special case, right? How we can use this, the framework of extension to develop our own extension to solve these problems. Okay, so let's see our design approach. Okay, to develop an extension and see. Okay, so here the approach is, we call this event-driven detections. When I say event-driven, the approach is we don't we not rely on the statistics from the shared memory. We basically hooks inside the query. Okay, every query execute, we hook inside into that. My extension will hook inside to the query and inspect this. Is this query is doing any type of bloating to the system? If it is doing bloating, track those bloatings. to a spatial cache or spatial global memory, we call it as the global brain for this vacuum booster, okay, who will be tracking those table and their bloating counts. And this particular the global memory or this particular shared memory will be monitored by a dedicated process who will be keep monitoring this particular global memory. And the moment they observe that the bloating count reached to a threshold, it immediately take action instead of taking a reactive, it take basically proactive manner, okay, and it create a dynamic worker and who will do the cleanup for you immediately for that. So see, it is not like this is completely removing your auto vacuum. Is basically is try to give this design is more on giving a complementary to the auto vacuums, so that they together can work together, and it can this vacuum booster can take some of his high load activity to his hands, so that things can move, I mean the performance can improvise in the systems, right. So let's start implementing this concepts. So as I told you in the starting, there are 4 files, important files. One control file. So let's start with the control file implementations. So if you see the control file of the vacuum booster, the first thing you give is the comment, what is your particular extensions try to do that, okay. So we give this informations, and what is my default version of my extension, and if my extension somebody is getting loaded by the Postgres, which location is present, those information you give it. Along with, you can see there is something called relocatable is equal to true. It means that so by default, when your extension get loaded to your system, or somebody have started using your, have installed your extension using create extension command. So create extension, my extension is vacuum booster. So the vacuum booster provide a list of interfaces to user in terms of table, view, or the procedures, whatever they have implemented, they have given to that, right. Those by default will be installed to the public schema. Now you are telling relocatable to means what a vacuum booster implementation will do is, the moment you tell no, I want my all this database objects, whatever you supported, you put it to my own schema. So you can specify, the relocatable can handle that part, okay. Now the second file I told you is the bridge, is the SQL file between user and the core engine of the extensions. So this engine basically, so in my case, I want to show you to the user that what are the tables I am tracking in my system, okay, who are undergoing a bloating, I am tracking those, and those detail I am giving in terms of a view to the user. So this will be the interface to the user. Whenever the user want to see my extension or to view this detail, they can use this query, okay. So this is nothing but the SQL file, okay. Now let's come to this the real implementation, the core engine part, right. So is it in the starting, if you remember, I told you like whenever you you in the shared preload library, you have told now my extension need to be loaded. So during the start of the Postgres load your SO and search for a keyword called as PGinit in your SO in the library. So this is the PGinit hit search for. So in this PGinit, you need to register all your callbacks. When I say callbacks or hooks, it is nothing but Postgres given you some amount of global pointers in each of the modules you have. Either in the query, if you see the query module, for example, in query module you have either in the parser, you have optimizer, planner. In every subsystem, he give a pointer to you. So what does this pointer do for you is that the moment the query execute or your execution start, if you tell that you have given your register there, then it deviate this flow towards you and it start executing your flow, right. That is the use case of basically the PGinit part is that basically you are doing the registrations. So basically using this, we are registering to the system like, see, I am going to use I want to expand Postgres using my features, so please register me. So in this case, what is I am going to register? If you see my design, first I told you I need a global shared memory or a shared memory which is the global brain for my extension. So I'm telling, okay, this is my global shared memory. Please allocate some memory for me. So that registration I'm doing here. I'll show you that how implementation I do partially. I will show you that part. And the same time I'm telling, no, for this global memory I need some locks, because this is need to be protected. I will also need to inform to the Postgres, like please also take care of these parts. Plus, because this particular design, if you see in the executor layer of the query, so what I'm doing is I'm hooking to the executor subsystem of the Postgres, and I'm telling, so every execution happen, the query happening. So you come to my place, I will inspect your query and see that do you create any data tuples. If you created data tuples, I will inspect you and track in my in my memory whatever I have created for this particular extension. Okay, and I need a worker who will be keep monitoring this shared memory created by these extensions. So let's see this. So all this detail, see in the 17 line number, I'm putting this registering to the systems plus this executor flow, whatever I'm telling, like this registration, I'm doing this. So all detail, let's see this in the flow level, how it is happening it. So as I told you, like before we start the Postgres started, we need to tell that Postgres that I need a shared memory. So those registers, the structure of the shared memory I have to inform it, right. So in this case, to track my bloated tables, right, what I considered a very simple structure where I am tracking only 1000 tables, just for the hardcoded I have done it. So where this particular tracker is, basically it will track those rel IDs who have those have this bloated tuples. Okay, I will track it, and those entire structure need to be created in. So the shared memory need to be created, right. This is the function implementation I will give it to him. So in the line number 10, when I register, this function will be called during the when the Postgres allocate the memory, shared memory for during the start time, right. It will call our function and it will allocate the shared memory for us. Okay, plus we need to know some amount of you need to handle because this is a critical section, you need some amount of locking techniques, right. Also I am telling to the Postgres in the line number 14, you also give me a lightweight lock, okay, and a name lock, so that I can protect this status. Okay, so this is what I normally try to register, so that during the start of the Postgres, basically it allocate memory for us along with the other shared memory that allocated by default by the Postgres itself. Okay. Now go to the if you remember, one of the I would try to hook is the executor subsystem flow. So in the executor flow, I want to see every query that get executed in the by the executor. What I am to do, I want to inspect this query. So what I am doing is, I am hooking to the executor flow. Once what will happen is, during execution time, so I will track those queries, okay, and if they create data tuples or they create bloating tuples, right. So what I'll track it inside my shared memory. That is nothing but the global brain for this entire vacuum booster. So this is how you can see the 12 number line number. I'm updating to I'm taking a log, exclusive log, because I'm doing a write operation. I'm tracking which table and who have done bloating counts. I'm just keep tracking those parts. And there is another call is you have the monitoring process. If you remember, like in the first line in the PG init time, I told to the Postgres, you create a monitoring process. This is the definition for it. So this monitor process will be, it will be keep monitoring, okay, to the entire the shared memory created for this for this vacuum booster. It will keep monitoring the the shared memory, and the moment he identified that one of the table got bloated to the threshold level, right, it immediately what it will do is it will create a dynamic memory. So you can say in the line number 10, what I am doing is when line number 8, I will keep checking that do you reach the bloating threshold. If you reach, you create a dynamic worker for me and start cleaning those the particular table. So the dynamic work is it will clean your table, the bloated table, and once it finishes, it exit from the system. Plus, the entry in the in the shared memory will be removed by this by the dynamic worker process. Okay, so this is how that using this power of extension, infrastructure, we can develop such a we can add extra facilities or extra capability to our systems, right? So if you see one end-to-end things like this ecosystem, so what we did is we start hooking to the executor, so that every events we are tracking it. The moment we found there is in the query right, they create dead tuples, keep adding those tables, and there dead tuples counts in the global shared memory, and that is we call as the brain. The brain will be tracking it, and so there is a manager who is a background worker we have created it, who will be keep observing this brain. The moment he observe, he will keep supervising it. The moment he observe, there is some amount of it reached the particular table reached to a certain threshold, right? Start creating a crew member, do the cleanup. So crew is nothing but the dynamic worker will create it and start cleaning those things. So this is the entire ecosystem we can create it, right, and give extra facility to the Postgres systems, right. So this is what we can do with we can develop it with the extensions, right. Now let's understand like what are the important things you have to take care when you are developing extensions in C. Okay. So the first thing you have to do is you be a good citizen. So when I say good citizen, you are not only the one person who is implementing extensions. So there are extensions who are also running in your systems, okay, and in the same flow they have also implemented like you. They have hooked into that. So when you, because there is a global, basically what Postgres give, he given a pointer to you, just put your function pointer to there, like it will call automatically. So you have to maintain the chain. So we call this as hook chaining problems, okay. You should maintain the hooking problems. You should not lose that hook. So you have to maintain that hook chain. So if you see my previous things also, I maintain that hook. I think in the executor flow, I have, I think, no, here. You can see the line number 18 and 19. I can, what I do is, not only I hooked to the executor flow, after finish up my execution, I also tell, no, there is a, if anybody is in the, have using this executor flow also, please call them also, so that they don't lose their mechanism, whatever they have implemented it, right. This is what we call as, you be, kind to others extension also, so that we complement each other, okay. So, sorry. The second part is the process integrity. So don't create process by yourselves. Don't call folks inside your extension. Use the infrastructure that Postgres have given to you. Don't do that part. So what you do is register everything, all worker, the dynamic memory, the processes through Postmaster itself. So Postmaster will monitor you, okay, so that whenever they require, if any crash happen, it has a power to handle it, right. Then second part is safe, the memory safety, okay, how you allocate the safe memories. So when you want to use any memory or any type of shared memory you wanted, or any logs you wanted, do this creation during PGConf. You inform to the during starting of the Postgres, you inform how much memory you needed. How, if you need a log, you inform to the Postgres. The Postmaster will take care of all these details. So you will monitor everything, so that any problem, any type of I will tell you a special case where this problem can happen. So so it will track all these details. Okay. Then second part is when you, so typical C programmers, what we do is we should not blindly believe anything. We should validate the OIDs. Even if the pointer you accessing those range, you should validate properly. And if you have any, see in my case, I have a dynamic workers, I have typical background workers. So those should be they should be signal aware. So because Postgres communicate each process by sending signals, right? So should be signal aware, so that any type of problem happen, they can go for a shutdown properly. Okay, and when you are writing logging also, use the interface Postgres provide called elog, ERR port, and use proper labelings, and you distinguish whatever the log context you are writing, distinguish between your extension logs between the core logic logs, so that it will make difference for the administrator to easily distinguish from where it comes from. Okay, so that's all from my side. I think anything I have questions, I can answer it.